All right, okay, here we go. So take your seat and let's finish the second half of the game. So this is the summation or summary of the equation that we just derived. You understand that? So important one is this one. Okay, and if you have some memory space, try to remember the second one. Okay, this is the one that I ask you to remember. All right, so we use the computer to do the simulation and draw all the figures. It looks like this way. See, and this is a very old stuff. 0.6 micron. Okay, this is from the Stone Age. Okay, I tell you what. When I took my VLSI course in 1987, okay, I used a 2 micron process. Right now you use 0.18, right? That is 10 times smaller. And this company is dead. It's AMI Australia, Austria something, microelectronic. Never mind, just example. So they have a very typical process. Zinc oxide is 100 mTrons. Remember this one. This is mobility of electrons. Very threshold is 0.7 for the 5-volt systems. So plug in all the numbers and draw the figure. You can see this one. So you see that for every blue curve, you find there is a special point where it is left-hand side. You will see the curve like this way. It's a linear, or almost a linear. This is the resistor behave. At a certain point, okay, the line become flat. Okay, it will become a fixed current because this is current. So that means no matter how VDS is increased, at a certain point, the current is fixed. The current is fixed. The only difference of these 5 curves, okay, is that the turning point of each curve depends on what the gate voltage is. Let me repeat again. All the turning points, elbow points, okay, or we call the saturation point in the textbook, depends on what gate voltage is. So, but the thing is, we have a very brief summary. They have a similar behavior. Okay, so we increase the VGS from 0 to 5 and use the minima size following the lambda rule of 4-2. This is excuse me. This is the width. This is the length. Width and the length. And okay, then you calculate the beta. You plug in the numbers, and these are the you see that 3.9 is the primitive of the zinc oxide, and this is free space constant. Okay, and divide by this one, width over length, is what you get. Okay, 120. And let's check. This is for the NMOS device. Let's check the PMOS device. Let's see what happened. PMOS device is totally opposite. Okay, totally opposite. So I'm going to erase the border. Erase over here. You're going to see something really interesting. Okay. This is a two-dimensional space. This is where this is N device, N transistor. And this is a third quarter. You're going to see similar stuff, but totally opposite. It'll become this way. This is P device, P transistor. Very interesting, huh? The reason why? Okay, because it's quite easy. Excuse me. Because in the N device, in the vertical, we apply positive voltage to attract electrons. But instead, for the P device, we like to attract what? Electric hole. So we need negative voltage. That is why it's negative. So that it can attract holes. And the current direction is also opposite to that of N device. So negative VGS, negative current, okay, negative VDS. So that is why the P device, the plots were sitting in the third quarter of the space, Okay, so for the P device, the mobility, depends on how fast the hose is. But unfortunately, the hose mobility is lower, much lower, 2 to 3 times lower than that electrons. The electrons. So that means if we're given the same size of transistors, N and P, they don't have the same current. Which one will be bigger? N device will be bigger. And P device current, which is smaller. And what is the ratio? It's about 2. It's not exactly 2. It's somewhere between 2 to 3. But usually we take 2 because it's easier for students to remember. So given the same size, we are going to have only half of a current from P transistors. So we're going to do about, if we want to balance it, we have to increase the size of the P transistor in order to have a same magnitude of currents. So that's usually why we increase the PMOS size, PMOS transistor, to be double of the N devices. All right? This is why. Remember this. And the typical number here is 120 for the hose. And let's check it's 350 for the electrons. It's about 3 times. So the textbook suggests that at least 2. So the next question is how to calculate the capacitance. The capacitance, parasitic capacitors, is everywhere. It does not just exist between the gate and the channel. As long as we have a PN junction, we have parasitic capacitors. So we have to understand why other parasitic capacitors exist and how to estimate that. So the capacitance, show up whenever we have any 2 conductors, and they are separated by insulator, and then that's where the capacitor is. Gate to channel is very important. That's here. So that this capacitor creates channel charges, and these charges are used to do calculations and the data movement. This is important. But besides that, source and drain here. Source and drain. Source and drain. Remember, you learned that we have a PN junction. This is N. This is P. So technically speaking, we are going to have a diode over here. PN junction, right? This is N plus. This is P. So we have a NP junction. Similarly, we're going to have NP junction over here. NP junction, of course, we're going to have over here. All of these are called parasitic capacitors. They have a capacitance to body, then it's called a reverse bias diode, just like what I draw over there. It is called the diffusion capacitance. You cannot get rid of it. It's always there. It's nature. As long as we have junction, we have capacitance. The only thing you can hope is that it is smaller, very, very small compared to the gate capacitance, that we can ignore it. In most of the occasions, we do the design. So it's a diffusion cap. Diffusion cap is parasitic capacitor. So right now we are going to formulate it as well. So this is how it is formulated. All right, check here. CGS, gate to source, is pretty easy. Epsilon, area over thickness. This is 1. And then the people like to make it simpler. So they combine the length with a gate, unit gate, gate capacitor to be this one. It's called the capacitance per micron. Per micron is typically about every 2 micron we'll get 2 femtofarad. This is how it is simplified to estimate, okay, the the capacitor, parasitic capacitors. This is called gate cap. All right, then this explains why the designer is valuable. Okay, now I'll give you some example. When you are a freshman or a sophomore, you know that, okay, you are going to design transistors like this way. Okay, let's assume we have a transistor. They are sitting on top of each other. Okay, and for this one, this is, this is drain to source. This is drain to source, and you show them together. This is gate 1, the gate 1. Okay, and because you want to design an AND gate. This is the basic for the AND gate. AND gate. Okay, when you are a sophomore or a freshman, the professor will tell you, you just consider the connection between this transistor is ideal. They can be made of metal. Okay, no problem at all. Okay, so it's good. Okay, there is no bad effect. Just assume it is a perfect connection. But when you want to realize this thing on silicon, okay, then you have different options. For example, if you do the first way, okay, step by step, the first one, okay, the first case. Let me draw over here. So on the planar here, you're going to do this way. Okay? And this is to the ground. This is to the top. You just rotate it by 90 degrees. You understand what I'm saying? So basically, you want to show them together. Okay, you have 2 devices. So what you do? Okay, I'll just follow what I learned from the schematic. So I'm gonna do, okay, short ring. Okay, over here. Okay, this we got to make a connection, and we have a metal piece over here. Metal. This is metal. Okay, we got to drill a hole. Drill a hole. So it's a V hole. This is V hole. Okay. Will it work? Yes, it will, because the current will go this way, going up, going down, going horizontal, going down, going this way. This is how it works. So this is the side view of this case. Side view of this case. You got one transistor, just like one over on top. You have another transistor sitting in the bottom. So you fabricate it, you design it using 2 different transistors. Will that work? Yes, it will, logically. But when it comes to performance and the cost, see that you have to go through, a very long way to send a signal over here. Okay, you're going to the 2nd floor, then going down to the first ground floor and travel to the right. The second thing is that there is a minimal requirement of a space between 2 transistors. So you got to sacrifice a space over here. This is to be sacrificed. As we said, the area means the cost. So not only this design is slower, it's more expensive. It's more expensive. So that is why, okay, we can use a better design in the middle. Why don't we just, merge these 2 together? Because all we need is just a short circuit. That's all. So a better designer, he will merge these two vehicles together, make the signal going up and going down in the same hole that will save one vehicle. But the thing is, it's still, redundant. What do you want to set it up and set it down? Okay, it's ridiculous. It's just running for nothing. So the best design is that we don't need it anymore. We just merge those two diffusion together, merge them together. So we don't need nothing like this, okay? All we need is to follow the design rule. I use a big one. That's it. Okay. Then you don't have to pay the price of extra holes, extra metal, okay, and extra space limitation between two devices. Okay. Even though these three designs, they all match the original schematic design and match the gate of functionality, but when it comes to cost competition, that one has the advantage, not this one. But for those beginners, fresh IC designer, they always follow this protocol. Okay, I can do the one by one, make sure that nothing wrong. Yes, you can do that in this semester, that's fine. Okay, I don't blame you because you want to make sure the functionality is good. But if you like to make yourself a little better than others, than before, why don't you consider other design alternatives? See, so in this way, not only we save the price, we also reduce the parasitic capacitance. Because the larger the area, okay, the more capacitance you create. Okay, we use a small diffusion nodes. We have a smaller capacitance. We are going to save at least half of the CGT for uncontacted. So this is a very good design compared to this one. These two. So we got to think about how to merge things together. However, you still have to follow the design rules. Okay, so this is the final and the better summation of the behavior of a single device. Okay, this is a schematic. This is the side view of a P-channel device. Okay, you have a gate, you have a source, you have a drain, you have a channel, and follow the square rule. Okay, this is a size, mobility, VGS minus VTH square, and this is what you're supposed to get over here. And this is a symbols over here. Okay, if you don't draw the arrowhead, it could be a source or drain, either way. But if you do draw the arrowhead here, okay, arrowhead goes to source. Okay, that shows where the low voltage is. And for those information or digital designer or computer engineering or information engineering, they always use a symbol which is considered as a switch to represent, to simplify a real transistor. But my advice is that, okay, you can do that when you are doing the logic design. But when you are going to fabricate or design your chip, it's better to follow these two symbols. Okay, this is for N switch or N devices. And let's see its counterpart. I think it's P switch. Okay, this is a behavior. Sorry, before I forget. All right, and this is quite important. You got to remember this one. So the source goes to the lowest voltage, right? So if we want to discharge, so this is VDD, this is VD, and this one, okay, I'm going to erase this one. Okay, now this is a very important concept for you to understand. Okay, let's assume this is a device that you want to turn it on and off. Okay, right now this is VG is equal to VDD, system voltage. And this one is VDD. Okay, so there is a voltage drop. The drop here says VDD. So certainly, when this is high, the current will go down. All right, no problem at all. It's perfect. Now the problem is a lot of students, okay, mess up at the beginning of design. When they say, I have a VDD at the gate, this won't be turned on automatically. No, it's not. Okay, in this case, if this side, the terminal here is not grounded, it is VDD. Then there is 0 volt, right? If you have a 0 volt, how can you push the electrons to move? You understand what I'm saying? It's impossible. So if you want to make it work, at least you got to have some voltage drop. Remember the one that we use over here? It's a VTH or VT. It's a threshold voltage. That stands for the minimum voltage you need to turn on the device. So you want to make it work in the in the saturation region. This one cannot be this high. It got to be at least this lower. Then the device can be on. Is that clear? At least this amount. So that is the reason why, okay, when we have a VDD over here, okay, and we have VDD over here, this one cannot be VDD. So when it is doing the charge, okay, we send the electrons to the other side. It cannot be as high as VDD. If it is high as VDD, it'll be what? It'll be cut off. Nothing will go through. So the maximum voltage you can get to use the switch to charge a capacitor using an transistor, the maximum voltage you can get is VDD minus VTH. That's it. That's the maximum I can get. However, if you use this device to discharge a capacitor, okay, here is VDD, right? And this is VDD. Then you want to discharge it because this is 0. Then you have a very big voltage drop. It'll be perfect. It'll be perfect. So we want to do the discharge. Then the blue line directly goes to the bottom. Okay, you have a perfect discharge. So in this case, we have a conclusion. I'm going to erase this one. If in this case, we are going to have a very important N transistor, N device. Okay? N device. Pass VDD, pass high. Pass low. Okay? When one pass high, okay, want to deliver a signal, is VDD equal to high. Equal to high. You want to pass high? Yeah, you got high, but you got VDD minus VTH. You got the weak one. Yes, you still pass 1, pass high, but this high is lower than what you expect. On the contrary, if you want to pass 0 over there, okay, so this is ground. Ground equal to 0. What you get? You got ground, 0. You got a strong 0. You got a strong 0. Okay, because 0 is always there. Okay, perfect. So the N device is very good to pass 0, pass ground signal. It's a little bad to pass 1 or VDD. So if you are smart enough, we are going to get the total opposite operation of P devices. P switches. See? The equation almost the same. Besides, we have a negative threshold voltage for the P devices. So you got to use the absolute value. Okay, if you do that, okay, in the third quadrant will be flipped to the first quadrant over there. All right, so the equation is the same. But sorry, I made a mistake. This is micro P. This is P needs now earned. This is my bad. Okay, I forgot to fix it. Okay, so it should be the mobility of electrons. And see, the symbol is here. See that? It's a circle. Or you use it this way to show what the direction is. If the arrowhead goes again, that stands for the P devices. Okay, and for the P device, 0 means on, 1 means off. So it's totally opposite. And the interesting part is that let's see this. Okay, it's opposite. See that? If this is 0, and this is VDD, and it's going to be very good to pass the 1 over there strong because there is a voltage drop. It's minus VTH, or minus VDD, so it's lower than the VTH. So it's definitely that it will pass the 1 very good. But however, you want to use that to discharge, and you have a big problem. Because this 0, 0, 0, this one cannot be 0. It's impossible because we need at least a minus VTH over there. So this one, you cannot, okay, put it down to the ground. So for the P device, it's totally the opposite. Okay? Pass 1 and pass 0. This is bad. This is good. You got a strong 1, okay, but a poor 0. Because you cannot use it to discharge, okay, the capacitor totally to the ground. It's impossible. Okay? So now we have a conclusion. Based on the feature of these devices, you want to pass this is very good at pass 0. This is very good at pass 1. So if we want to combine them together, so we are going to have this together. We got it based on this feature. We have the first gate in our design. Okay, we use the P device on the top to pass 1 because 1 stands for the VDD, and this is our load. Capacitance that's over there. And we're going to use a N device to pass 0. That means to discharge it. Okay, so we are going to have our first design, aka this is a very famous and also the most fundamental design in digital. It is called an inverter. Why it invert the design this way? Because we take the advantage of these features over here. When the Vin, see that? When the Vin equal to high, what happened? This one will be closed. This one will be closed over there. See that? It will be closed. Okay? But when this is high, we are going to discharge. That means we pass the 0 from over here to here. Right? So we have a Vin equal to 1. We are going to have VR equal to 0. Okay? On the other hand, if we have a 0, based on the feature that we derive, the N device will be blocked. Nothing will happen. Nothing will happen. But we are going to turn on the P devices over here so that these two terminals are connected together. So the power supply will be driven to charge the load. Just the one over there. to charge it. And this one will be good, V1. And you are going to have a full swing of 0 to VDD. This is the inverter. And the symbol of this one is the one you see before. It is a triangle, follow a small circle on the top, on the tip. So this is the first design you learn in VLSI inverter. Is that clear? Right? Okay, the second important thing of the inverter design is that, remember we said if they are the equal size, which one has a bigger current? This one, right? Because it has a bigger mobility. This one has a smaller. So in order to balance the current, we have to increase the size of the P device, the width. Okay, let's assume the length is the same, the width, to be double, okay, than before. So that we are going to have a 2-to-1. 2-to-1. If we increase the size, the width of the P device, then we are going to have about the same current from the power supply to the ground. So this is a very basic design. We are going to have the first one. This is the inverter. Then we are based on all the equation we learned. Oh, okay, that's why we are going to have a 1-to-2 or 2-to-1 inverter design. This is our first one of this course. Is that clear? Not so hard, right? So these are all the reasons why we have ratio design. Okay, and this is the equation that we learned as before. And it is called the first order long channel models. It's the same thing. It's called a Shockley first order IV curve. The reason why I put it over here is that when I graduated in 1992, okay, and in 1980s, the Berkeley, they developed, Berkeley University, California, okay, they have the first version of the SPICE simulator. And the funny thing is, when I had an interview in AT&T, I bumped into the guy who write the program. I still run into that guy. Okay, it's extremely smart. About 35 years ago, it's a long time ago. Well, so I consider that was a legend. It's a legend, okay? Well, that guy we consider is the position of that, the SPICE simulator creator is almost the same as Michael Jordan in basketball history. Without the effort of this guy, we are going to still get lost in the jungle of IC design. Okay, even though that after that, a lot of guys, a lot of programmers to improve the efficiency of SPICE simulator, but we gotta give the credit to this guy. I mean, they are from Berkeley. Okay, give the credit to these guys. Okay, they are the pioneers. Okay, so let's go to find out what is the difference between the reality and the theoretical result. Well, unfortunately, the first order equation is not that accurate, okay, when we use advanced devices, advanced process, and this is an example. Okay, if you're using 0.18, that's a 180 nanometer, the one I use in this class, we consider is somewhere legacy. But if you use the IBM process 65 nanometer, which is still the one of the major process right now, you can see how upset, okay, how big the difference is. See that? Based on the second order Shockley equation, we get the black line, black curve over here. But the funny thing is that if you run a simulation and the measurement, okay, you got to see the measurement. This is a blue curve. And you can see how big the gap is. The error is terrible. It's unacceptable. Okay? And this is VGS 1.0 by by measurement, and this is a theoretical result by the square law equation, and this is 0.8, 0.6. When the VGS is getting smaller, the accuracy is improved. So that means we have a very big issue in terms of simulations. When we use a very simple equation, it's hard. The reason is quite simple. Very simple. Okay, I'll tell you why. It's just like our life, okay? These equations, they're only good for long channel device. Very old device, old process, legacy, long channel devices. Okay, like 180 nanometer, which is 3 times larger than the 65 nanometer. It's a long channel device. So if you use a very old process or legacy process, then you got no problem, use this one. But when you are using advanced 65, right now in my lab, most of students use 40 nanometer, 40. And some students use 28. And I have a project sponsored by TSMC. This kit uses 16 nanometer, which is 10 times smaller than the one you use. All these equations, they don't stand anymore. Okay, all the equations that we see that in textbook don't stand anymore. They got to go to very high order polynomials to approximate the accuracy. So this is only good for this course. This is only good for the textbook and the practice. So if you find out that in the future that the simulation result does not fit or meet what you expect, don't get upset. It's not your fault. Okay, because the model is too simple. Is that clear? All right? Okay, don't get upset, but in this course it's still good. Okay, another cruel fact is that, okay, we always assume that when the VGS is 0, there is no current, right? But unfortunately, in reality, it's not. We always have leakage. Just like in your house. Every house has a leakage of water. Okay? Every city has a big problem of leakage of water. It's leakage everywhere. See that this is the figure to show you what. Okay, here this is VGS equal to 0. We still have a very teeny tiny current, 27 narrow amp. Narrow stands for 10 to the minus 9th order. Very, very small, but it's still there. Why is it meaningful? Because right now, if you're, the number of your transistors on your design is over 10 to the 9th, then all the leakage current, you add them up together, that will become 1 amp. 1 amp is large. Okay, you're doing nothing, you just waste 1 amp all the time. That's scary. That's scary. Okay, do you know how much current you need in your house, every floor? I'll give you a number. If you have, if sometime you go back and check the electricity box in your house, technically for every average family, every floor, in every room at least, like a 20 amps to 30. That's all. That's all. If you happen to have an air conditioner like that, you might increase to 50 amps. 50 amps. Think about that. The leakage power here could be as high as 1 amp. That's scary, because the microwave, the one you use to heat up your food, only costs you 2 amps. So the IC with 10 to the 9th power, 10 to the 9th devices is almost like it's almost like half a microwave. Very scary. Okay, so this is the leakage current. All right, and this is a video that I want to show you to see how the transistor works.
a metal oxide semiconductor field effect transistor, MOSFET, is made of p or n-type doped silicon. In this example, the substrate is composed of p-type doped silicon. On this substrate, there are electrons, shown here in white, as well as holes, known as electron holes, shown here in green. Through ion implantation, two n-type regions are formed. The term n-type signifies the fact that adjacent to the normal silicon electrons, there are additional electrons which are free to move around, shown here in red. An insulating layer is needed. This is typically produced with silicon dioxide. Above this, a layer of aluminum is applied via vapor deposition. Finally, a second layer, composed of silicon dioxide, is applied, in which contact holes are created through etching. The transistor is now ready. Taken together, there is a p-type substrate with two strongly n-type regions, as well as electrical contacts, which provide the transistor with the necessary current and voltage potential, known as the source, gate, drain, and bulk terminals. Source and bulk are often connected to each other, so they share the same source of current. The objective is to control the flow of current between source and drain. This is accomplished with the gate. If there is no voltage potential at the gate, there will be no current, because no carriers of current are available between the two n-type regions, shown here in red. However, should there be a positive voltage potential on the gate, a positive electrical field builds up, which attracts electrons in the p-type layer and repels holes. These electrons form an n-channel that can carry electrons from source to drain. It should be noted that the current between source and drain can be increased through raising the voltage potential, which leads to a stronger electrical field and thereby a larger n-channel. Since no current is able to flow between source and drain when there is no potential on the gate, this type of transistor is called enhancement mode MOSFET. MOSFETs are increasingly used in integrated circuits, for example those used for microprocessors. Since only electrons or only electron holes alone take part in carrying current, this type of transistor is considered to be a type of unipolar transistor.
Okay, so this is how the video. This is to show you how the transistor and what the operation is. Okay, so based on the understanding of these features, transistor features, we can move on to discuss more. So right now we understand how an inverter is designed. And why do we need to change the size of the PMOS? Because we like to balance the current, okay, for the charging and discharging. Another application is that, okay, we can combine the features of these two devices together to come up with another design, which is called the TG, transmission gate. Transmission gate. Oh, okay, sorry. Before I go to the transmission gate, I'll tell you. So the inverter over there, I almost forgot, sorry. Okay, I'm going to remove this one. So the inverter, if we have a single inverter, we just copy it and cascade them together. Okay, see that? We have a signal here as A, and this inverter will get an A bar, right? And we get an A. So the signal itself can be repeated, okay, using even numbers of inverters. And the even number of inverters we call this buffer. Buffer uses a single triangle to stand for. That means A gets in and A gets out. Okay, it's called a buffer. All right? As long as they are even numbers. For example, we can add another 2, okay, to get a long buffer. And the question you might ask, why do we like to have a long inverter chain? From time to times, you need to delay certain signal so that the signal can be synchronized with others. So basically, the buffer means to create delays. Create delays. Okay, because the delay here will be proportional to the number of inverters. Okay? And then some signals are fast, some signals are slow. When you want to do this calculation together, you need to delay those faster signals, okay, so that they can be used to synchronize with those slower ones to do the computation or other management. Is understood? So when you learn how to design the inverter, then the next step you should know that inverters can be used to create or design buffers. The only difference is that how long is the delay you need. All right? So the delay based on the numbers and the delay of a single stage inverter. That's all. So this is for the buffers. Another alternative to take advantage of the NMOS and transit is this one, switches. It's called the transmission gate. If we combine the NMOS and the PMOS together. So this one, when the VIN is coming over here, when this is a very bad, not a very bad, high signal that with VDD, because one of them is good in passing one. Which one? Over here. So when the signal sees the signal is high, and this one is good at the passing high signal. So signal, of course, will take it here because it is a low resistor to this guy. And electricity is just like water. They always select the path with least, resistance. So when this is high, the signal will go this way. When this is low, the signal will go this way because they always select the low resistance path to pass the signal. And this is a symbol over here. When the C is high, of course the C bar is low. So both of them are on. If C is low, C bar is high, then, the C bar is low and this is high, then it's stopped. It's closed, it's cut off. No one will be allowed to pass. Okay, it's totally closed. So this way we call the transmission gate. TG stands for the transmission gate. Transmission gate.